This video describes the Process Capability Analysis Statlet. It's new in Statgraphics Centurion version 17. This statlet assists analysts in performing a capability analysis. A capability analysis compares the distribution of a data sample to specification limits. There are two main approaches to demonstrating process capability. The first is the calculation of capability indices and DPM, defects per million. The second is the creation of statistical tolerance limits. I'll be demonstrating both of these approaches using the statlet. The statlet also handles data from both normal and non-normal distributions. As an example, we're going to look at some data from a manufacturing process that measures the resistivity of electronic components. The specification for resistivity is 50 to 550 with a target value of 250. We've taken a sample of 100 components from the manufacturing process, and we'd like to estimate how capable we are of meeting that specification. I've loaded the data into the Statgraphics data sheet. Once a day, a random sample was taken from the manufacturing process and the resistivity measured. To do a process capability analysis, I'll go to the top menu and select Statlets, Process Capability Analysis. Resistivity contains the data to be analyzed. Date identifies when the measurements were taken. The lower specification limit is 50. The nominal or target value is 250, and the upper specification limit is 550. When I press OK, the window will open up and a lot of interesting information will be displayed. Statgraphics has taken the 100 observations and plotted a histogram of the data. It's also superimposed on the histogram a normal distribution. A normal distribution with the same mean and standard deviation as the data. You can see along the top of the graph that the mean is approximately 235.3 and the standard deviation is approximately 71.9. The tall vertical lines show the location of the specification limits and the target value. The shorter vertical lines are located at the mean of the data plus and minus 3 standard deviations. We would normally hope that the mean plus and minus 3 standard deviations would lie completely within the specification limits. That's because the plus and minus 3 sigma limits contain about 99.73% of the population. We're doing fine at the upper end, but the lower 3 sigma limit is below the lower spec. In the right margin of the graph, you'll see a number of statistics calculated to summarize our capability. You see a p-value for a Shapiro-Wilk test and a p-value for a Kolmogorov-Smirnov test. I'll talk about those in a few minutes. You also see capability indices, both short-term and long-term capability indices, calculated to summarize how well we're doing with respect to the specification limits. Let's talk about some of the capability indices that Statgraphics displays by default. The first index is called CP. It's the ratio of the distance between the specification limits to 6 times the estimated standard deviation of the process. In order for our plus and minus 3 sigma limits to lie totally within the spec, CP must be at least 1. Most of the time, though, we'll want CP to be considerably greater than 1. You'll hear rules like it should be greater or equal to 1.33, or greater or equal to 1.5, even greater or equal to 2. Unfortunately, CP has a couple limitations. First off, it requires both an upper and a lower specification limits. There are many times when you have only an upper or a lower, not both. Secondly, it doesn't take into account the location of the sample mean. In fact, if the mean is far from the target value, we may be putting a lot of our product outside the specifications, even though our CP statistic may be quite large. An index that gets around these limitations is the index CPK. It's calculated by taking the smaller of two quantities. It first calculates the difference between the sample mean and the lower specification limit and divides by 3 times the estimated sigma. It then calculates the upper spec minus the mean and divides that by 3 sigma hat. If both of those limits exist, it'll take the smaller of those two calculations. On the other hand, if you have only a single spec, it'll take whichever calculation can be made. It turns out that CPK is always less than or equal to CP. You'll hear similar rules for CPK, such as it should be at least 1.33 or at least 1.5, depending upon the product you're producing. A third index that gets directly at the quality of our product is DPM. DPM stands for defects per million. It calculates how many items out of every million I'm producing are likely to be outside of my specification limits. To calculate DPM, we take the area under the normal curve below the lower spec and add the area under the normal curve above the upper spec. If there's only a single spec, we'll only take one of those areas. Six Sigma practitioners identify processes as having world-class quality if DPM is no greater than 3.4. A final index that I like is called K. K measures how far off target our process is. The way it's calculated is this. We calculate the sample mean x bar. If it's greater than the target value, then K will be the difference between the sample mean and the target divided by the distance between the upper spec and the target. If the mean is less than the target, then K is x bar minus t divided by the distance between the target and the lower specification limit. Basically, K measures how far we are off center as a fraction of the way to the nearest specification limit. I need to make one more important point, and that has to do with how the process sigma is estimated for each of these capability indices. There are basically two ways to estimate the process sigma. The first is to estimate it from the moving range of the data. That is, by looking at the differences between consecutive observations. If we plug an estimate of sigma into our equations that we obtain from the moving range, then we're estimating the short-term capability of the process. Another way to estimate sigma is by using the sample standard deviation S, the ordinary standard deviation of the n observations we've obtained. If we plug that sigma into these formulas, we estimate long-term performance of the process. By the way, it's common practice to call the indices CP and CPK when we're estimating short-term capability, and PP and PPK when we're estimating long-term performance. If the mean of your process is not stable but tends to drift, then your capability can be considerably better than your performance. Let's return now to the Statlet output. You'll see in the right margin of the graph calculations of short-term indices, those are capability indices, and long-term indices, those are performance indices. You'll see the values for CP, CPK, PP, and PPK. There's not much difference in our data between capability and performance because our mean is quite stable. You'll also see the estimated defects per million. It's around 5,000 defects per million. The value of K equals minus 0.07, which indicates that our mean is below the target value by about 7% of the distance between the target and the lower spec. The capability indices we've calculated only make sense if in fact the normal distribution is appropriate for our data. It's very important whenever we do a capability analysis that we check the assumption of normality. That's why there are two additional statistics in the right margin of the graph. There's a Shapiro-Wilk test and a modified Kolmogorov-Smirnov test that can tell us when the normal distribution is not appropriate. The Shapiro-Wilk test and Kolmogorov-Smirnov test are called goodness of fit tests. They test the hypothesis that our data come from a normal distribution. The Shapiro-Wilk test is probably the most powerful test for normality. The Kolmogorov-Smirnov test is a less powerful test, but it can be used to test whether the data come from not only a normal distribution, but other types of distributions as well. Modifications also exist that make that test more powerful than it used to be. For both of the tests, small p-values, typically p-values less than 0.05, will cause us to reject the hypothesis that the data come from a normal distribution. You can see on the Statlet output that there's a p-value associated with each of the two tests. The p-value for the Shapiro-Wilk test is 0.0000. That's a very strong rejection of the idea that our data could have come from a normal distribution. The p-value for the Kolmogorov-Smirnov test is not an exact p-value. The output, though, does show that the Ks p-value is greater or equal to 0.10. In that case, we would not reject the assumption of normality. Since the Shapiro-Wilk test is the more powerful test, we'll have to conclude in this case that the data do not come from a normal distribution. That means that these indices, the DPMs, the CPKs, and so forth, do not properly describe our process. If you look closely at the histogram, I think you can see that it is not a symmetric distribution. In fact, the true distribution rises fairly quickly to a peak and then has a rather long upper tail. To model this data, we're going to need to take one of two approaches. We're going to need either to go up to the Statlet toolbar and try a power transformation. The slider here allows me to raise data to different powers, which will change the shape of the implicit distribution. We also have a pull-down menu from which we could choose a different distribution. Let me talk for a moment about power transformations. They're a very powerful way to handle non-normal data. Given a random variable y represents resistivity, we can create a transformation by taking y, potentially adding some value delta to it, and raising the result to the p power. As a continuous function of p, we would take y plus delta and raise it to the p power if p was not 0. However, if p is 0, we'll instead take the natural logarithm of y plus delta. It turns out that in many cases, if you pick some p between -5 and 5, you can find a transformed metric y prime in which the transformed values are well modeled by a normal distribution, even if the distribution of the original data are not normal. Typical values of p might be things like 0.5, which would correspond to a square root, or -1 for p, which would correspond to a reciprocal transformation. The addend delta is often set equal to 0. But if any of your data values are 0 or negative, you'll need to add a little something to them before you can either raise them to a power or take a logarithm. You'll see the effect of applying different powers if I use the slider on the toolbar. You'll notice if I bring the power down, let's bring it down to 0.5, that's a square root, that the implicit distribution of the observations becomes skewed to the right. It's normal in the square root metric, but in the original metric where I've plotted it here, it's a highly skewed distribution. You'll also notice that the Shapiro-Wilk value has gone up to about 0.03. Let's continue applying the transformation. Let's change the power now and bring it down to 0. 0 corresponds to a natural logarithm. The distribution is now even more skewed, and the Shapiro-Wilk p-value is 0.6756. That's well above 0.05 and indicates that in fact the logarithms of resistivity may be well modeled by a normal distribution. To find the optimal power transformation, I'm going to call on another Statgraphics procedure. I'm going to go back to my main menu and under Statlets choose Power Transformations. I'll put in resistivity and press OK, at which point a second window will open. The second window shows what's called a quantile-quantile plot. It shows on the y-axis the quantiles of the data. That is basically the data sorted from smallest to largest. On the x-axis, it shows the equivalent normal quantiles. If in fact resistivity followed a normal distribution, the points plotted on this graph should fall approximately along a diagonal line. 95% limits have also been added to help you judge whether the points are sufficiently close to the line, so you could decide whether or not to assume a normal distribution. It's quite clear from the shape of the points that they don't fall along a straight line. To apply a power transformation and find the optimal power, I'll now go to the Statlet toolbar and press Optimize. This will invoke what's called the Box-Cox procedure and use it to determine the best value of P. It turns out in this case, the best value of P is minus 0.4, and you'll notice that will give me a Shapiro-Wilk p-value in excess of 0.9. I'm now going to minimize the Power Transformations window and go back to the Process Capability Analysis. I'll bring the power down to the optimal value of minus 0.4. You can see the very high p-value for the Shapiro-Wilk statistic. You see the implicit distribution, which is now quite skewed. You'll notice various other changes to the plot as well. The short vertical lines, which initially were located at the mean plus and minus 3 standard deviations, are now located at the equivalent of plus and minus 3 sigma. By equivalent, I mean they're located at the same percentiles as plus and minus 3 sigma would be in the case of the normal distribution. They're actually determined by first looking at the distribution of the data in the transformed metric, taking the mean plus and minus 3 sigma, and then invoking the inverse transformation to put them back on the resistivity scale. Unfortunately, the upper equivalent 3 sigma limit is now quite a bit above the upper specification limit, although the lower equivalent 3 sigma limit is now good. You'll notice also that the short-term and long-term capability indices have changed. Some have gotten better, some have gotten worse. The important thing is, though, that these capability indices are now based on a model that adequately fits the data. Another approach to dealing with non-normal data is to select a distribution other than the normal. I'm going to go to my Statlet toolbar and bring that power back to 1. I'm then going to go to the pull-down list and see what other distributions I could choose. Actually, there's a fairly long list of distributions that could be used to do my capability analysis. To determine what distribution to use, I'm going to go back up to the main Statgraphics menu. I'm going to select Describe, Distribution Fitting, Fitting Uncensored Data. The data to be fit will be resistivity. The distribution fitting procedure gives me a choice of 45 different probability distributions to choose from. I'm going to start by assuming a normal distribution and press OK. However, when the list of tables and graphs appears, I'm going to check the box next to comparison of alternative distributions. This will cause Statgraphics to fit various distributions to the data and sort them in order of how well they fit. The list shows that the largest extreme value distribution would appear to be the best out of the dozen or so distributions I tried for this data. At this point, I'll go back to Process Capability Analysis and change my selection to largest extreme value. You'll see now the results of fitting this particular distribution. As you can see, the largest extreme value distribution is also a skewed distribution. It's defined by a mode, in this case estimated to be around 203, and a scale parameter, in this case approximately 54. The equivalent 3 sigma limits are located at 101.51 and 559.7. The lower 3 sigma limit is well within the spec, although the upper 3 sigma limit does sneak a little bit outside. You can also see modifications to the short-term and long-term capability indices, including the defects per million. In terms of judging whether the largest extreme value distribution adequately models the data, the Shapiro-Wilk statistic is no longer relevant. That's simply a normality test. However, the modified Kolmogorov-Smirnov test is now testing the assumption that the data come from a largest extreme value distribution. The p-value is greater or equal to 0.1, so the fit is, again, acceptable. As I said at the beginning of this video, calculation of capability indices and DPM is one of two possible approaches for determining whether my process is capable of meeting this specification. The second approach is the calculation of statistical tolerance limits. Statistical tolerance limits bound a specified percentage of the population of items I'm producing at a specified level of confidence. For example, a 95-99 tolerance interval is a range of values that we can be 95% confident contains at least 99% of the population. The Process Capability Analysis Statlet will calculate statistical tolerance limits for various distributions and also for situations where you apply power transformations. It doesn't get around the problem of having to select the best power or the best distribution, but once you've made that decision, you can calculate the tolerance limits. When calculating tolerance limits, you can choose between two-sided tolerance intervals and one-sided tolerance bounds. I'll now return to the Process Capability Analysis Statlet one more time. On the Statlet toolbar, I'll select tolerance limits instead of sigma limits. The short vertical lines will now switch from being the equivalent of plus and minus 3 sigma to being statistical tolerance limits. By default, there'll be 95, 90 tolerance limits, meaning that I'm 95% confident that at least 90% of my population is within those limits. Let's increase the population percentage and bring it up perhaps to 99. Okay, there's 98, and we'll bring it up to 99. Oh, overshot it just a bit. There we go. I now have limits in which I'm 95% certain I will find at least 99% of all the electronic components that I'm producing. A very common way to demonstrate capability is to calculate these tolerance limits. If they're completely within the spec as they are here, then you decide that you are in fact capable of meeting the specification limits. I think you can see that this statlet is a very easy to use yet powerful tool for performing a process capability analysis.